And the title of today's webinar is Artificial Light Balance for Different Varieties of Tomato. So this talk is being recorded, and recording will be sent to the audience. My email is also here at the bottom of this presentation, the first page. So if you have any questions later on, you can feel free to send me your questions. So I've given this talk a number of times in a few conferences also. So this is also a repeat of the same talk, plus some additions, which may be useful to some of the audience. We also have a Q&A session at the very end. In case there are any questions, you can ask me at the very end. So this work that we did was a collaboration between our company, Allied Scientific Pro, and Mr. Ian Godfrey, who is a horticulturalist, and he lives in Tampa, Florida. So all the tomato cultivating and LED work was done by Ian, and the analysis and writing the paper was written by me. So he has a lot of experience in dealing with horticultural projects. So we really used his expertise in this project. So the outline of my talk is about different varieties of tomatoes, and the basic of it is that 3 different varieties of tomatoes were planted in 3 different environments, which were the outside garden, greenhouse with supplementary lighting, and an LED chamber which had no access to outside light, and there was only LED as a source of light. So we are comparing the results of these 3 together. So I'll talk about different varieties of tomatoes, the photoreceptors, the usage of different wavelengths for photosynthesis, morphology, and then about the environment, the outside garden, greenhouse with supplementary lighting, LED chamber, changing the spectrum throughout the day and throughout the season. And then we would compare the growth results as far as flower clusters, morphology, average internodal distance, stomata opening, leaf color, and nutritional testing is concerned. And then we'll have some conclusions. So the different varieties of tomatoes that we had was number 1, F1 Trust, which is an indeterminate variety. By that we mean that it only grows in a single vine. It's a large round tomato. It's immune to complication, very resistant to pest and insect attack, and it had previously been planted in the outside garden. Number 2 was Indigo Cherry Drop. It's a black cherry tomato. This is a rare variety of tomato. It had never been planted before in the outside garden in Florida. And number 3 is Gold Rave. It's again a rare variety tomato, golf ball size, orange plum tomato. Never been planted in the outside garden before. What are the optical equipments that we used as far as the sources of light and detectors were concerned? For detectors, we used the Lighting Passport, a standard Pro. It's a spectroradiometer that works in the region 380 to 780 nanometer, and our company distributes it. It gets the spectrum through Bluetooth, and it's a smartphone spectrometer. Number 2, SRI 2000. It's another spectroradiometer, but works in a wider range of 250 to 850 nanometer, and our company distributes it. This is because we wanted to measure the sunlight, and we needed to do UV measurements, and therefore we used this one, mostly for outside garden and greenhouse. And As far as the lights are concerned, there is the, let me just get rid of this for now. There is the Solar System 550. It's a LED panel made by California Lightworks. It draws 400 watt electrical, and mostly blue and red light. I'll show you the spectrum of this later. Secondly, we had the Solar System 275, again from California Lightworks, 200 watts. And the reason for this is that each season requires a particular lighting. You can't shine too much light during the vegetative season. That's why we use the lower power LED panel. And then we had the 100 watt electrical draw Solar System far red for end of the day treatment, again from California Lightworks. So these were all the sources of light that we had. So let me talk a little bit about the SRI 2000. So this unit has the range, as we said, from 250 to 850 nanometers, and I'm giving some examples of this. It's very useful for horticultural applications. For example, the HPS lamps, the spectrum, you can see it here. It has a very strong peak at 830 nanometers, which is not normally measured by normal spectroradiometers. But our spectroradiometer can measure that. Here is a measurement done from a quartz halogen lamp that you can see goes up to 850 nanometers. So this spectroradiometer could measure this line for HPS. And who knows what the effect of near infrared light is on plants. So if somebody wants to research this, this would be a really good source. In the low end, I measured the 266 nanometer laser with the SRI 2000, which is at the end of this scale towards the left. And you can see that it shows the laser peak at 266 nanometers. So that is the, you can say, the UVC region even. So some cultivators want to use UVB, especially for cannabis. UVB has some benefits to produce additional HTC. So this spectroradiometer is quite useful for measuring the wavelength and intensity of light in a wider range. So let's talk about the electromagnetic radiation of photoreceptors and plants. Okay, so this diagram shows the electromagnetic radiation all the way from gamma rays to radio waves. We know gamma rays have very small wavelength, high frequency, and as we move towards the right, go through X-rays, UV, visible, infrared, microwave, radio, the wavelength gets larger and larger, and the frequency decreases. Now, the visible range of the spectrum is from 400 to 700 nanometer, defines the human vision, and it's only a small section of this spectrum. Now, the plants also respond to a little bit wider range of a spectrum, starting from UVB somewhere all the way to far red, so about 320 to 780 nanometers. And there are several photoreceptors that are responsible for these interaction of light and plant, and these are UVR8 for the UV region, which we are not discussing because we didn't use any UV sources. Cryptochromes, they are sensitive to blue light. Then you also have green cryptochromes. Then you also have phototropins that are responsible for green light, and they are responsible for the effect of phototropism, where the plant is looking for the source of light, like a sunflower who traces the source of light. Then you also have the phytochromes, and there are two types, PR and PFR, that absorb in the red and far red region, and they have very useful effects for plants and responsible for several functions, which I'll describe later. So the reason nothing shorter than this to UVB affects plants is because actually the ozone layer blocks that, and we don't get any of that you can say UVC radiation on the ground because ozone layer blocks it. So plants didn't evolve any sensitivity to it. And as far as the higher radiation concerned, they have very small energy to affect the photoreceptors. So that's why we are only restricted to this region from 260 around there to 780. And we have taken this diagram from the reference by Fulton and Carvalho. Photoreceptors and control of horticultural plant traits from University of Florida, which is the main support and main reference for this presentation. So here is a picture of the spectrum of the sun taken with the SRI 2000, and you can see that we are detecting up to 325 nanometers down here, and here up to 850 nanometers. The solar spectrum has some absorption lines due to oxygen and water, and it's basically a black body, but it's affected by these absorption lines. On the left diagram, you see the ground level and the top of the atmosphere, and you can see that 80% of UVA gets through, and only about 20% of UVB gets through, and none of the UVC. And this is just due to the blocking by the ozone layer. Now, the Phytochromes, Cryptochromes, and Phototropins are shown here. Phytochromes, they're pigment sensitive to red and far red. They're responsible for floral stimulation, stem elongation, circadian rhythm, and shade avoidance. I'll talk about this a little bit later too. And there are two types that convert back and forth among each other. So far red or PR absorbs a red and turns into far red. So PR is actually the inactive form, turns into far PFR, which is the active form. And then the other PFR either absorbs far red, or if it sits at night, it converts back into PR. Then you have the Cryptochromes, which are the blue sensing pigments controlling plant height and fruit size. And you also have the Phototropins. There are also blue sensing pigments responsible for phototropism, which is the idea of looking for the source of light, where you could maximize the amount of light that is received for photosynthesis. So for PFR and PR, quickly, I said that red light is absorbed by PR and turns into PFR, and at night you could either shine far red or let it sit at night, converts back into the inactive form. So the ratio of PR to PFR is quite important for the plant to sense which season it's at, and basically decide when it's time for its flowering. So it's very easy to fool the plant by shining PFR or shining far red radiation so that it thinks it's a different season. So this ratio plays an important role as far as the circadian rhythm and as far as floral stimulation is concerned. There's also the shade avoidance response shown here. So one plant is shown here, is uncovered. The ratio is 1.2 between R and FR. The other plant here, the other bigger plant has covered it, it's been shadowed. So because the far red radiation mostly transmits through the leaf, the amount of far red does not change that much, but red is heavily absorbed by the taller plant, so the ratio of R to FR decreases. And once the plant senses decrease in this ratio, it knows that it's being shaded by another plant, and tries to go in a different direction to come out of the shadow. If the sun was covered by a cloud, both R and FR would go down, so the ratio would not be affected. So this is another function of that. So let's talk about the usage of different wavelengths by plants. The blue wavelength, I've shown here blue, green, red, and far red. Mostly 450 nanometer is for photosynthetic chlorophyll A and B absorption. Very important. It helps keep tomato vines short and compact also. This is morphology of the plant, hence more fruits in the same area. So blue has a big effect on not only photosynthesis, but also morphology. Leaf color could become darker when the blue levels are high. And the green wavelengths also participates in photosynthesis, but not as much as red and blue. And the other good point about green is it bounces off the top layers of canopy and therefore reaches the lower levels. It also is useful to have a bit of green light for visual comfort, because it's very difficult to work under the pinkish light produced by the combination of blue and red, and you can't identify damage in the plants and take a picture and work there. So addition of a little bit of green will help. Now, red light, primary wavelength that stimulates photosynthesis, chlorophyll absorption, essential form of light balance, contributes to flower formation, fruit development, contributes to general health. And far red at 730 nanometer influence the phytochrome and changes from its active form PFR to inactive. Hence this ratio changes, and it could stimulate flowering. It also stimulates the stretching of stem. So let's talk a little bit about the environmental factor where this growth was done. It was in Tampa, Florida. You can see here in the picture. So Tampa, Florida, on the west side of the Florida, and the location of the growth was very obviously, it's very humid. It has very humid summers, temperatures in the mid 80s. The only variety that was cultivated there before, as I mentioned, was the F1 Trust, and there's a need for daily watering due to high temperature and humidity, and heat and humidity cause drooping of the leaves. So here's a picture of the outside garden, and the sunlight photo period was 12 hours, 80-degree temperature, and watering had to be done by hand every day. And we actually took a spectra using a lighting passport at 5 different times: in the sunrise, late morning, mid-afternoon, late afternoon, and sunset. And you can see that there are clear changes in spectrum that are taking place. For example, in the sunrise, there's quite a bit of far red. You can see these peaks, and very little blue. And this is all due to scattering of light in the atmosphere, because the sun is traveling through a longer path in the sunrise. Then when the sun comes up, there's more blue comes up and less far red. You can see over here. Of course, the intensity is also changing. You should have to pay attention to the scale here. And I'll show you another plot that shows the change in intensity. And then moving on, as we approach the sunset, again, the far red comes up and the blue goes down. What is this black line over here? This is just the McCree's reference spectrum that shows a typical curve for the best light source for the photosynthesis. This was done in the 1970s, some experiments, and the average of 22 plants, average response was measured by Professor McCree in Texas A&M University came up with this curve. But you know, there are many much more aside from photosynthesis. There's much more to growth of the plant. There's also the morphology of the plant, and the McCree curve does not describe. Here is again red to far red ratio and red to blue ratio, and here's a paper that shows that the red to far red shown by this parameter zeta actually is low at the beginning of the day, and then it decreases, and then it decreases at the end of the day. And we also saw that not the beginning of the day, because there were a lot of clouds as shown in here when the measurement was done. But at the end of the day, we saw a decrease. And the blue R to blue ratio actually is a reverse. It's high at the very beginning of the day because blue level is low, and then it becomes stable, except for this point, which is an exceptional point due to cloud scattering. And then at the end of the day, it comes up again. So this is consistent with what we saw. Now, if you look at the variation of PPFD throughout the day, and this is somewhat related to how we adjusted our LED lamps, or what was the rationale for changing the intensity of our LED lamps, you see that there's quite a bit of change in intensity, and also the spectrum also changes. So at the very beginning of the day, here you could say 8 p.m. sunset, at the end of the day, sunset. For the sunrise, we didn't really do a measurement for sunrise, but 8 ppm, PPFD, 8 a.m. There's very little light. It should be shown in here somewhere. So when, for example, if you look at the blue PPFD 3 p.m., a higher intensity, much higher intensity, about 7 micromoles you get at 650 nanometers. And you also see that the change of spectrum is changing. The amount of red is really high. At the far red is really high towards the end of the day, and at the blue is pretty low at the beginning of the day. I'll show you a relative intensity plot that shows this much better. This is a relative intensity plot where maximum of each of the spectra is 1. So you're all normalized. And you can see at 8 a.m. There's very little blue here, this thick blue line here, very little blue. And then over here, 8 p.m. sunset, also very little blue, but they both have very strong far red radiation. However, if you go to 4 p.m. Over here, or 10 a.m., you can see at 10 a.m. the blue comes up. Blue levels are much more, and there's much less far red radiation. So the spectrum is changing, the quality of the spectrum is changing, and the intensity is also changing. Although we didn't have any control over the quality of the spectrum, we changed the intensity in the LED lamps so that we should follow this natural pattern, which I'll talk about later. So the greenhouse with supplementary lighting, you can see there's a picture in here, and this is a supplementary lighting. Again, a 12-hour photo period, but as far as the sunlight is concerned. And then there were 2-3 hours where we turned on the supplementary lighting. It was from 7 to 10 a.m. and 4 to 7 p.m. So the spectrum is a mixture of the LED lamp and the sunlight, which has been measured by SRI 2000 here, and also by the lighting passport over here. And it's the black body radiation by the sun superimposed on the red and blue peaks of the LED. There was no far red usage in the greenhouse. And you can also see there's a fan here that mixes the weather, the air, so that, you know, it produces a breeze so that the leaves could get a little bit colder, so reduce their surface temperature, which helps their growth. As for the LED chamber, This is the general spectrum that we have used, a very strong red peak and a smaller blue peak, the very little green for visual comfort. This is my colleague Ian Godfrey, who's measuring in the pinkish area of the LED chamber what the spectrum is. And you can see there were several different areas, LED chambers, and there were different pots in here for growth of the plants. This had an 18-hour photo period, so 6 hours more than the outside garden and the greenhouse. Also had a dehumidifier, CO2 supply, air conditioning that kept the temperature around 70 degrees. So had better environmental condition and more light as compared to the outside garden. So let's look at the spectrum that was adjusted for different times of the day. This was programmed in the LED units. So we had 3 hours sunrise, 2 hours late morning, then 8 hours mid-afternoon, 2 hours late afternoon, and 3 hours sunset. So the intensity is changing, which is not apparent unless you look at the y-axis numbers. But I plotted all of them over here on top of each other, and you can see that the sunset and sunrise, the blue and green are lower, and the mid-afternoon is the higher intensity. So we start with the low values, and then we ramp it up to mid-afternoon, and then towards the end we'll go down again. This is just to simulate what nature is doing. Also, you need different spectrum for different seasons. During the vegetative seasons, you cannot afford to shine too much light on the young plant because it could potentially burn it. But when it gets into flowering season, you need to put more light. So here, for example, late morning seedling and vegetative state, we use the lower power SS275, but in the flowering stage, fruiting stage, we use more powerful SS550. And this line over here, or this curve, represents the far red, whose intensity did not change. So it's a good comparison to see how these intensities are changing from the late morning to mid-afternoon. So here, for example, you can see for the vegetative state, the intensity of this far red is almost half the SS550 peak. But if you go to the fruiting stage, if you go to the mid-afternoon, the intensity of this is probably 1/3 of the SS550. So this shows that from late morning to mid-afternoon, this intensity has increased. And also the fact that from the fruit stage to from seedling to fruit, always there was an increased intensity, and that is shown in here. And far red, I'll explain a little bit later. So right here, actually, the far red is shown, it's centered at about 735 nanometers, and we only use it as the end of the day treatment for about 15 minutes. This would not cause stem elongation because we wanted to have more compact plants, but it would stimulate flowering since the duration is short. So this was one fact about the far red. So next, the growth results. What are we discussing? The flower clusters. Next, we will have the morphology, number of fruits. Next, we have the average internodal distance, and then trichome clusters and stomata opening, and also leaf and fruit color, and finally nutritional values. So these are all the things that we are comparing between the tomatoes grown in these 3 different environments with different light sources. So as far as the flower clusters are concerned, the LED chamber produced the best flower clusters, and here's a quote from a LED magazine. It says blue light encourages vegetative growth in plants. It often increases leaf production and vegetative density. For this reason, plants are grown under lights high in blue wavelengths during the initial stages of development. A high leaf number count and low internodal lengths are expected. And this is exactly what we observe. Here are the three different wines from three different plants. And basically, you can, my colleague has counted the number of flowers in each branch of these wines. So 9, 11, 14, 9, 14, 16, 14, 15, 16. And these are much higher compared to the numbers in the greenhouse and outside garden. And 100% of the flowers turned into fruits for the LED, but this did not happen for the other two environments. Here are also the three pictures: F1 Trust, Indigo, Cherry Drop, and Gold Rave. They all produce very nice flower clusters. Now, morphology, number of fruit. You could also see drooping happen in the outside garden, not as much in the greenhouse, and very little or nothing in the LED chamber. And this was mostly due to high temperatures there. The LED chamber was mostly air conditioned, so temperatures were better. So you can associate the drooping with the temperature. But then as far as number of fruits are concerned, the LED chamber produced the maximum number of fruits. So here, for example, you see there is there's a ruler here, and we have counted the number of leaves in 5 inches. So you have 4 leaves here in 5 inches, and there are only 3 leaves in the outside garden. So greenhouse, F1 Trust, only 85% of flowers develop into fruit, but outside garden only 75%. So LED chamber produced the maximum number of flowers that turn into fruit. Average internodal distance. Again, there's a paper here that supports our idea that due to the presence of blue light, there was smaller internodal distance. And so these numbers that you can see in this table are much smaller than the greenhouse and the outside garden. And by internodal distance, it's represented here, where this branches out. Leaf and fruit color. You can see here that there was the leaf and fruit color was a different. The leaf color is different. This is the leaf that has been taken out of the LED chamber, just taken out of the LED chamber, and compare this with what is from the outside garden. So you see there's darker colors. And papers support the idea that having more blue light, which was the case for us in case of the LED chamber, produces more darker colors. There's other effects as far as trichome clusters and the stomata opening. So the LED chamber, this is pictures we're taking under a microscope. There was more trichomes in the LED chamber. Trichomes act as a defensive mechanism for the plants to stop insects to attack them. So having more trichomes is useful, it's more resistant to insect attacks. Also, stomata openings are more in the LED chamber as compared to the other one. Again, these pictures were taken using microscope, so the plant could breathe better and exchange gases much better. Okay, so next is the role of green light, and this is quite important, what the role of green light is, because there's been a lot of controversy over, whether you need to put more green light and use the full spectrum, or it's better to not use the green light. So one factor is that the McCree spectrum shows that green light helps in photosynthesis. That's true. It helps in photosynthesis, but there are some adverse effects in as far as the morphology is concerned. So one factor, and this is something that my partner has experience, is a horticulturist. Ian Godfrey, my partner, has experience, and he's in touch with a lot of different horticulturalists, and they also experience that, is that use of too much green would delay the flowering process. So here you can also see from this paper by Folta and Carvalho, it says addition of, this is a quote, addition of green light can inhibit the blue light response, the blue light mediated destabilization. Green light has been shown to repress flowering. So if you shine too much green light, your flowers, your fruits basically turn to stay in the vegetative state for too long, and they would not go into the fruiting stage so easily. So that's one adverse effect. The second effect is that the stomatal opening is less when you use green light. So the green light counteracts the effects of the blue light. The blue light wants to open the stomata, the green light wants to close it. So as a result, the breeding is better when there is more stomatal opening. So that's not a good effect. And the third effect that is shown here is that the dry mass of the plants that were grown using the green light is less as compared to the ones who did not have a green light. And this was supported by this paper by Folta and Carvalho. So when plants were grown under visible light, including the green, the dry mass was lower, no matter how much the total fluence rate increased. So some of these effects are not desirable. I think particularly the fact that it will delay the vegetative process and will not transition to the flower, to the fruiting process, fruiting stage so easily. That's an undesirable effect. Now let's look at the leaf and fruit color. These are from the three different environments. Clockwise from left is the LED, greenhouse, and garden. And for gold, this is for indigo cherry trop. Gold Rave, also you can see from LED, greenhouse, and outside garden. And this is before the harvest, this is after the harvest. And one can see that the LED chamber produced larger fruit clusters, it had richer colors, larger fruits, and also more bountiful fruits. So fruit clusters are here, and these are the size are also bigger and they're richer in color. Now, it would have been a really great idea to measure the nutritional values of these three different tomatoes, but it was not done, unfortunately, due to shortage of time. And this was taught after the harvest was done. But we wanted to pay attention to this issue, so we got a hold of some similar type of tomatoes just to have a baseline values for nutritional value, nutritional content of this tomato. We got a hold of these Campari tomatoes, which are also indeterminate hybrid greenhouse tomato plants grown in Mexico, and sent it to these Midwest laboratories in Nebraska to get some measurements of the nutritional values, so that next time around when we do measurements and we grow tomatoes, we should have a baseline value and compare these nutritional values. So tomatoes are famous for having vitamin C, vitamin K, the antioxidant lycopene, and also you can say lycopene and folate, vitamin B. So I want to mention that my partner in this work, Ian Godfrey, is there, and he wanted to say something in here. I just saw a note there. You can, Ian, you can unmute yourself, or you could wait till the end of the presentation, and then we can talk about that. I think it's better if I finish this, and then at the end you can, we can make you the presenter, and you can add to this. So we only measured the ascorbic acid, vitamin C, just show the values at 22.5 milligrams in 100 grams. Basically, that's the value we measured from this tomato, which is similar to F1 Trust. And there's the basic test of moisture, protein, fat, ash, carbohydrates, and calories. But next time around, when we grow different varieties of tomatoes, we definitely want to measure vitamin K, vitamin B, which is folate, and vitamin C, we already did. And if we can measure the antioxidant lycopene, it would be great. This particular lab is not able to measure lycopene, but we have to find a different lab that does that. Here is actually their device where they are measuring or weighing the amount of the uh, particular sample of the tomato. Now for future work, uh, what we are planning to do for the next round of our cultivation, and this is what my colleague Ian Godfrey will be doing, is that uh, we want to compare the white light as a source of LED with the blue and red light, which is provided by California Lightworks. And we want to put these two samples of tomato in the same LED chamber with the same environmental condition. So 18-hour photo period plus air conditioning and humidity control and CO2 supply, so that everything else is the same except for the spectrum. So we already have this lamp from a company in California called LED Bloom Light, and it's a spectrum very much similar to the sun. And so we would just vary the spectrum and then compare the growth results. So everything else would be the same, because somebody could argue at this point that maybe you got bigger fruits, better quality fruits because you had more photo period. But we don't, all the literature that supports our work says that it's because the additional amount of blue that we used that we got, and probably some more red, that we got these good results. So, and absence of green as well. So these are all factors that we want to test in our next round of our experimentation. So in conclusions, we found that indigo cherry drops produce the best results in the LED chamber as compared to the other two. The LED chamber produced the best results as yield, flower production, and fruit size. Color of leaves and fruits grown in LED chamber were darker as compared to the greenhouse and the outside garden. The LED chamber flower clusters were most compact, and this was a desirable effect for us. We wanted to have more compact, and we associate that with the amount of blue light, increased blue light spectrum. It is possible to grow rare varieties of tomato in adverse environments. Previously, indigo cherry and the other variety was not grown there. Yeah, so this is possible to grow it in the LED chamber. Stomatal opening were widest in the LED chamber due to increased blue illumination and reduced green illumination. We show that with the microscope picture. Baseline nutritional testing of a similar tomato to F1 Trust shows 22.5 milligrams and 100 grams of ascorbic acid, which is just vitamin C. And we will compare this with our future measurements. And from each variety, we will measure it. And finally, for the future growth trials, nutritional content of tomatoes grown in different environments and under different lights, which are white and red-blue, will be measured and compared. So thank you very much for listening to this. And at this point, I'd like to ask Ian Godfrey, to my partner who did all the work, to come on. And Ian, can you unmute yourself?
I believe I just did, right? Can you hear me?
Yes, I can hear you. Yeah. Did you want to
Great.
ask?
Yeah, I might just add that we are currently at the stage of cleaning the lab. Everything is refreshed. We've upgraded a couple air sanitizers and some new oscillating fans. We have both chambers set up and cleaned and ready to go. And we are also, because the lighting situations are very similar for tomatoes and peppers, meaning the photo period is for both crops is 18 to 20 hours a day. They have very similar demands in the seedling stage and the production stage. I hope that I'll have enough time to grow all three varieties of tomatoes again, which are the F1 Trust, the Indigo Cherry Drops, which are the small black ones, and then of course the Gold Rave, which are the orange tomatoes. We are prepared to do all three of those. We have the seeds ready. And also I'm looking at varieties of peppers to include because we're going to have the chambers illuminated. We do have some extra space. And if we can sort of gather some more data as far as, the tomatoes, we may even include an additional fourth or fifth variety. So we have 5 varieties of tomatoes going. And we will also more than likely be doing a cayenne pepper called Red Flame, which I've grown before under a magenta spectrum, the heavy blue and the heavy red and a very little bit of green. I actually grew the Red Flame peppers with a LumiGrow back in 2016. So we're going to try the Red Flame cayenne peppers again. We're going to try a very spicy pepper called Helios, and then a rare pepper called Round of Hungry. And then we're also going to try a small purple bell pepper called Islander, which I've also grown before under a magenta spectrum, which was from the LumiGrow. So we're going to set up quite an interesting lab, hopefully beginning either December 1st or January 1st, so that we can grow everything, harvest everything, get some nutritional values done at the lab, and hopefully we can identify a lab for the last little thing that we would like to test as well. So we should have nutritional values of all 3 tomatoes, possibly even a 4th or 5th kind, to which we can benchmark to our tomato that we tested there in Reza's presentation. And then hopefully we'll also have 5 varieties of peppers that we can also use for our data collection. We'll essentially be using the exact same lighting recipes, in which case we'll be able to see if this magenta spectrum or the sunlight spectrum can grow peppers, and we'll see the nutritional values as well, along with some of the growth rates and harvest data, and see how everything turns out. So I expect that we will have quite a few research papers and quite a few presentations moving forward. And me and Rez are both looking forward to completing that for you guys and presenting that next year.
Yes, actually, it's really good, Ian. Thank you so much for adding this, because I had added that in the conclusion that we want to try the pepper somewhere. Tomatoes grown white and we measured. I think somewhere I added that. I don't remember where it is exactly, but it's good that you reminded us that we are not only going to grow tomatoes, we're also going to try pepper, and maybe we'll add also to the varieties of tomatoes, so it won't maybe more than 3.
Correct. That's exactly right. And I might also add that, the varieties of tomatoes that we grew for this last project were indeterminate, which is basically a vine variety. And essentially what I did was I wrapped them in sort of a spring type of shape, so that I could have a very compact area of plants rather than having the vines stretch out all over the place. One of the varieties that I was thinking about cultivating this next time is very similar to the F1 Trust in the sense that it's a large round tomato, but it's a determinate variety in the sense that it will grow in a bush fashion. So I expect it should have about 8 branches, all of which containing fruits, and that might be something interesting as well. So we should have a lot of new data concerning different types of tomatoes. We should have a lot of new data concerning these types of peppers that I've mentioned. And I'm also developing a strategic partnership with our very first city farm here in St. Petersburg, Florida, which is called Brick Street Farms. They have 4 chambers and they're growing over 25 strains of lettuce. And I brought the lighting passport in there. I've spoken to them pretty extensively. I'm working on consulting a couple issues there, and they're willing to allow us to take samples of their lettuce, do interviews as far as, whether it might take 15 days or 30 days or 45 days to reach harvest under which type of spectrum and which type of intensity. They have 4 different LED types that they're working with right now: a Philips red and blue. They have a Fluence, which has a high level of green. They have a Lumitex, which is a lower amount of green, but it's still present. And then they also have a sort of a custom built LED, which is just a strip of diodes, which is a red, a blue, a green, and then a far red. And they're seeing about 30 days from germination to harvest. And I hope that I might be able to go in there and take a few samples of lettuce harvests and do a nutritional value analysis as well, in which case we will be able to look at the 4 light sources and look at the tomato or the lettuce varieties, and then we will be able to show which type of spectrum created the best results and the most nutritional value in the lettuce as well. And the only last thing I might add is that they're also doing some data collection on shelf life concerning the lettuce after it's harvested. So since they're supplying fine dining restaurants right from their hydroponic farm, there's not much shelf life going on because the chefs come and pick them up right on the spot. However, it's a little bit different for stores and cultivating here at home, where we might harvest and thus need to wait, several weeks before consuming all of the lettuce. So they're also collecting some data on shelf life. And I hope to have all of the data put together here within about 4 months. So Rez and myself should have about at least 3 papers, one concerning tomatoes, another concerning peppers, and then the final one concerning lettuce, with the help of our strategic partner down here in St. Pete.
Right.
So we're looking forward to having this ready for you.
Right. Great, Ian. I want to add one thing, though, is that our belief so far in doing research, we did background research, we found out some material from different papers. Our belief so far is that it is better to just use strong blue and red with a little bit of green. But in the next round of trial, we're going to put this idea to test and use the white light with the LED bloom light to prove this. Okay, so I just wanted to sort of clarify our position here, that we believe that from all the background research we have done and from all the experience that Ian has had with other horticulturalists and the results he has seen, is that having a large amount of green light would delay the flowering and would reduce the stomatal opening and would reduce the dry weight. So, but we want to put this to test and actually see that this is the case. Am I correct, Ian?
Yes, Rez, that's exactly right. So we do know that it's highly situational. Even different types of tomatoes can have different effects from the same spectrum. However, throughout the past 3 years, I've done extensive research on tomatoes specifically, and sort of from a business perspective, how can we lower our costs and increase our productions? And what I found is that LED lighting is a key factor to do that, to optimize the business model of cultivating food. And when we consider cultivating tomatoes, which are a cash crop, although it's not an extremely lucrative cash crop, the operators are very straightforward in saying that they do not have any resources to waste. So when they purchase LED lighting, they very much want to see results. They very much want to know what to expect. And they sort of hope to have consultants on behalf of the LED firm helping them along the way, because implementing LED technology is still a new thing. So one of the major things that I tend to look at is, and the question that I tend to ask myself is, how many professional tomato cultivation facilities in North America use a magenta spectrum with high amounts of blue and red? And how many professional cultivation tomato facilities use a full spectrum LED? To which my answer would be, I have found 0 with a full spectrum LED being used to cultivate tomatoes, and the magenta spectrum I can cite over 150 facilities that are cultivating tomatoes for food, and research institutions that are helping these facilities cultivate food. So, that's essentially, I like to zoom out and look at the big picture. But again, there are rapid advancements in LED technology, and me and Rez hope to find out exactly what is going on here when we set up this new project. The only difference will be the light spectrum. All other conditions will be held the same, and we'll really be able to zoom in and see exactly what's going on stage by stage, day by day. And I'll have Rez here helping me evaluate the data. We'll be taking measurements as far as growth rates, harvests, nutritional values. So I really do believe at the end of this next project, Rez and I will be able to lay out the evidence concerning these varieties of tomatoes and peppers that we've chosen. And it should be pretty straightforward for everybody to understand and sort of look at and evaluate for themselves.
Right, definitely. So at this point, we have only about a few minutes, just maybe 3 minutes left. I was wondering if anyone else has a question. If you like, you could type it here, or you can just unmute yourself and let me know if you have any question. Are there any questions for either myself or Ian? Going once, going twice, going 3 times. So if you feel you want to think about it, you have some question come to mind later, you always feel free. You could email me and I'll forward the question to Ian as well. rmanny@alliedscientificpro.com is my email. And at this point, I would like to thank everyone to participate here, and also thank Ian for his additional explanations and all the work that he has done. He's the major guy here who has done the work, and he's the horticulturalist in this project. I'm more of a spectroscopy guy. What? Sorry?
Thank you very much. I appreciate that, Rez.
You're welcome. So thank you again for listening to our webinar, and hopefully we'll, in a few months' time, we'll have another one with much better results and more accurate findings. Have a great day, everyone. Thank you. Bye.
Thank you.